agenda today. So we're going to talk about TCP ownership, who owns TCP. We're going to talk about some terms so we're all on the same page. Receiver side factors, sending side factors. I'll give you a quick checklist, and then we'll hit a few other things that we really won't go into a lot of detail about, but you can investigate later on your own. Okay, so first, so why do we care about TCP? And further, like, who owns TCP? So when you get a call, the network is slow or the application is slow. Well, it could be a lot of different things, right? If you're like the network engineer who owns the infrastructure, not to say that you're a plumber, but like, are the pipes clean? Is the water flowing? Is it all connected? Are there leaks? Are you responsible for the quality of the water? Don't know. Is it the guy who owns the server? Is it the guy who writes the application? Is it the firewall guy? Who owns this? And this is something we can debate later over beers or something, but I don't know. I don't have a good answer for you. It's up for debate. When you dig down, you find out the issue is a TCP level issue. Well, who was responsible for figuring that out? Back in my career and trying to solve problems, I didn't care where the problem was. People always point fingers. I just wanted to stop the finger pointing as fast as possible. So I was happy to jump in, try to figure it out. So whatever thing you own, I would say it's a good idea to learn some TCP basics so that maybe you can jump in there, figure it out, stop the finger pointing, and move on. Because really, you have the physical infrastructure that clearly someone's owns, IP connectivity, clearly someone's own, firewalls, application, but the TCP layer, I don't know if I stole this from Chris or maybe this was his joke one time, that it's like the redheaded stepchild of the protocol stack, right? Learn as much as you can. You'll be able to solve issues quicker, and you can be the hero. So let's talk about bandwidth first. This is a screenshot off some internet site with a dictionary. So I'll read it for you. A measurement of the ability of an electronic communications device or system, such as a computer network, to send and receive information. So what does that mean? When you say bandwidth, right? You may, well, I have 100 megabits. I have a gig. You have some amount that capacity that you expect to have. Do you always get it? Probably not, but we have to start somewhere. So you have 100 megabits, whatever it is, that's the bandwidth that you have. So at home, how many people have like a gig or more at home? Do you really need it though? I mean, come on, a gig. I did, and then I was like, my Xfinity special ran out and it went up a whole bunch of money, so I dropped to like 600, and I don't know, I can't tell any different. But whatever it is you pay for, and it work if you have, circuits that you pay for. What about throughput? So, this is the actual amount that goes through the system that you're talking about. So you pay for a gig, maybe you only get 800. For your throughput maybe is only 800 or whatever it may be, but that's what you're actually getting. So the difference, right? The total amount that you should get, the capacity that, quote, you're supposed to get, bandwidth, but what you're actually getting, what we're really going to talk about today is the throughput. It goes up, it goes down. Why does it do that? I should be getting at least 100 megabits. I'm only getting 20. Why is that? I've seen so many, support tickets for these kinds of questions, and you have to dig in and figure out, why are you not getting some expected throughput? So what we're going to do is focus on one TCP connection, the throughput of one TCP connection, and talk about some factors there. So the first thing we'll talk about, bandwidth delay product. Who can tell me what BDP is? The relationship between latency and bandwidth. That's true. But what does that mean? You're limited by the distance between the sender and receiver for throughput. All true, all true. I just think of it as, what does it take to fill the pipe? If you're filling the pipe, that's the BDP, right? So distance and bandwidth are two, right? Exactly what you said, bandwidth and latency. Sometimes I think about like golf balls in a PVC pipe because I'm visual that way. What's up? No, it's not. Now it is. Yeah, so if you have like a short piece of PVC and you can fit one golf ball in, your BDP is one golf ball. If you make the PVC pipe longer, maybe you can fit 4 or 5 golf balls. Well, that's the BDP. Then if you make it, that's the latency, right? The length of the pipe is latency. The diameter around is the bandwidth. So maybe you can fit 3 in one go. And the more you can fit, the more BDP you have. That's kind of how I think about it. So that's where we're starting. That's sort of like, let's call it theoretically. Nothing is ever this simple or clear in real life, but we've covered one factor so far in terms of the throughput you can get. How much can you push, right? Throughout the conversation today, think about TCP. We always want to be sending. We want to send data as fast as possible. If we're not sending data, why? Why aren't we sending data? So we're going to talk about like the big rocks of that. There's always lots of little pebbles and little things that fill it in of reasons why. So we're going to talk the big ones, but why are we not sending data? We always want to be sending data as fast as possible. So far of the things we've covered, how much data can we send? I'm going to go ahead and do this one for you, but going forward, I want you to shout it out. So far, we've only talked about one thing, BDP. That is as much data as we can send. You can send more, but you'll probably lose some packets, right? So that's where we're starting. Now, the sort of scenario, the setup, if you will, of what we're going to kind of conceptualize this is we have a file of cat pictures, as you do, and it's 256K. So we're going to think about sending this 256K file between 2 hosts, and dotted lines mean it's unsent data, all right? So the factors we're going to talk about is how much data does the receiver think it can receive or says it can receive, and how much data can the sender send? We're going to keep it real simple today. Those are the 2 main factors we'll talk about. So let's talk about the receiver first. So we have on the receiver side, really only one main factor we're going to talk about today is the receive window. Most of you, I imagine, are familiar with the receive window. You might see it abbreviated RWIN or RWND, or if you see like code level things, you might see this SO receive buff, which is a thing that's used in programming applications for setting the size of the receive buffer. They all mean the same thing. It's the amount of free space that the receiver has to accept data, right? So I'm an application. Let me go ahead. I'm an application. I have a buffer that I'm going to read data from, and it has a certain size. The amount of free space in that buffer for me to receive data from TCP is advertised in every single packet that I send. It's in the TCP header. So we can all see this nice little picture. This is from the TCP header. You can see window size value, and it's highlighted there. It's an actual value in the TCP header that tells you the size that's being advertised. Now, that's not the real size that we're going to talk about, but it is there. And you can see that's the amount of free space it has to receive data. So now that is a 16-bit integer, so 64K is the maximum amount that can be advertised. Back in the day, I'm sure 64K was plenty, but it's not. In long time since, it has not been enough space. So RFC 1323 allows window scaling up to 1 gig. Now, it does have to be supported by both hosts for it to be used. And can anyone tell me, I'm kind of giving it away here, but where do you find the window scale factor? Yes, I heard in the options of the send packet. That is true. Where else can you find it? Nowhere. Nowhere. If you do not capture the three-way handshake, you very likely don't know what the actual window size is. So let me be very clear. When you're reproducing a problem and you're capturing data, so if you have a connection, maybe any kind of connection that is long-lived, if you can, make sure the connection's closed. If it's a map network drive, close that. If it's an application, maybe you close the application. Start your capture, then make the connections, then bring up the applications, then go to the website. You always, always want your three-way handshake. Now, So the window scale here is 8. It's a bit shift. So you multiply the value that was advertised here by 256. And so the real value is the one below it in brackets. That's the real TCP receive window. And if you don't have the scaling factor, you don't really know what it is. So if anything in square brackets is not really in the data, it's not in the headers, it's something that Wireshark is calculating for you, and it's just useful information to have. Okay. I think that's all I wanted to say about that. So we have 256K of data that we want to send. Of that, the first limiting factor we're going to talk about, we've already talked about one, BDP. Second, receive window. So can I as a sender just blast out 256K and be done with it? I mean, you can. It's not very nice. The other receiving end is telling me their receive window. If it's 64K, then I can send up to 64K, and I have to stop until I start receiving acknowledgements. All right, so now of the factors we've talked about, how much data can we send at one time? Again, always be sending data, never stop. So if we have to stop, why? We've talked about 2 factors. I'm going to give it to you. It's the minimum of the receive window or BDP, right? So now we have 2 factors in play, and it's the minimum of the 2. So let's have a look. All right. It has gone back to 2 different displays. All right. Can everyone see this in person and on the Zoom? I'll assume there's a lot of chats here. I don't know if they're important. Oh, they're talking about echo. Yeah. Everyone can see it. Love it. Hey, Betty. Wish you were here. Okay, so is the size of this okay? I can make it a little bigger. This is Wireshark. Not sure if you've seen it before. We're going to look at packets. So let's talk about a couple of things. We have a three-way handshake. Yay, me. I got the three-way handshake. So if I come down to the options, there's my maximum segment size. Again, only advertised in the three-way handshake. If you don't get it, you lost it. Here's my window scale. So it is 0. So it supports window scale. It's just like, I'm not going to bother. And same thing on the server side, window scale 0, maximum segment size, SAC permitted, all this good information that you definitely want to know. Three-way handshake, we can look at the latency. We know round trip time is about 97, 98 milliseconds. We know we captured on the client side because the delay is between the SYN and SYNAC. I'll let you think that one through. So we have some traffic flowing here. Now, someone says, hey, I have a throughput problem, and they give me a PCAP with conversations with 1 TCP connection. I say, thank you. You were so nice. Sometimes you get PCAPs people send you, and there's like 100 connections. You're not really sure what you're looking for. But hey, we have a throughput connection, a throughput problem. Here's the one I care about. Wonderful. So what I like to do is look at the stream graph under statistics. And a stream graph, by definition, is in one direction. So you want to click on a packet that has data in it that's being sent, which I've done. And I'm going to go to TCP trace, and it's not going to work. Does anyone know if this is a bug in my version? This happens all the time. I switch it and it's fine, but it always, no matter what I select, it goes there. Maybe I need to update. I think I am behind on the current version. So what all this is sequence number over time. Sequence number is a representation of bytes. So it's bytes over time, which is throughput, right? We want it to go as fast as possible. So the slope of the line indicates the throughput. If you see like flat spots, it means it's not doing anything. These are problems. Now looking at this one, just right off the bat, I'm like, ooh, that looks weird and bad. The more you look at this, the more you'll usually be able to spot patterns, behaviors just from looking at the picture. But we'll zoom in a bit. What we're looking at here is these little guys are packets. Each little one is a packet. I can click on it. It'll take me to that packet back in the other main window. The line below it are acknowledgements. So I sent this amount of data and then nothing happens. When it's flat and you don't see anything, nothing's happening. And then as this little stair step goes up, where my little Mickey Mouse hand is, these are acknowledgements acknowledging these packets over here. Like if you drew a line straight across, that's what's going on there. The line up here is the receive window. How much free space is in the receive window? So as long as there's space between the topmost packet and that line, you have free space in the receive window. So we can see we start out with a connection, we're sending data, we're getting acknowledgements, and then it's getting closer and closer to this line. And eventually, if we zoom in, they meet. So what does that mean? We filled the receive window. If I click on this packet here and I go back here, it didn't do what I expected. We should be pretty close, I think. Yeah, I just, I thought that would say like window full. It is pretty, so the window is 65K and we're a little under. Again, I would have expected it to show me window full, but we can come down a little bit. There we are. So you can see we're sending data, and then it says window full. Bytes in flight, which we'll talk about later, is the same as the window size. So we have filled the receive window, and we have to stop. We can't keep sending, or we overrun, the packets will get dropped on the receiving side. We receive an acknowledgement, and we send 2 more packets. So generally in TCP, it will ACK every other packet. So one ACK is ACKing 2 data packets. So if I get an acknowledgement like this ACK, I have now freed up space for 2 more packets, and I send 2 more, and then I wait. And then there's an ACK and 2 more. And you can see this behavior, if I zoom out a bit, you can kind of see this behavior. Let me go up here, play out right here, right? 2 packets, wait for acknowledgement, which is down here below. And we're sending 2 packets at a time, 2 packets at a time. So we have filled the receive window. Here we're just send a whole packet train out until we hit this line. We've filled the receive window, we got to stop. We have to wait for a round trip time for these acknowledgements to come in. So for every time an acknowledgement comes in, it's ACKing 2 packets, I send 2 more. I get another ACK, I can send 2 more. And we continue in that behavior. So if you see something like this, where the packets are hitting that top line, your receive window is too small. And if we go back, we can, as we pointed out in the beginning, this was contrived. This was a contrived example of essentially turning off window scale. But you go to the receiver and you tell them to increase the receive window to overcome this throughput limitation. Without having the send packet, can you reasonably assume the window scale? Thinking maybe look at the window size as it decreases and maybe. I'm trying to think if I've ever done this. Has anyone ever done that? Circumstantial evidence. You can't say for sure, but based on the behavior, right? So we haven't talked about all the factors. So you have to know, like, again, we always want to be sending data. If we're not sending data, is it receive window? Is it the other factors we're going to talk about? You kind of have to eliminate the factors, and maybe it kind of falls into it's a receive window issue. Answered live. Okay, now let's go back, pick up where we left off, and see if this is going to work. It probably won't. Are we good on the Zoom with the right screen? Yes? Okay, I'll assume unless someone will tell me if we're not. Okay, Well, that's what we're going to talk about on the sender side. It gets a little more interesting on the sender side. So first, let's talk about a concept that I've already mentioned, but we'll go a little bit more into it, and that's bytes in flight. We're going to talk about bytes in flight. We're going to talk about congestion window, where it gets really fun. I'll talk about send buffer, which is, the sending side, like a receive buffer. And I think that's it. Okay, so bytes in flight. Again, we've talked about the receive window. If I'm a sender, I know what your receive window is. So I'm going to send as much, I'm going to send and try to fill up your receive window, right? So I'm going to send as much data as I can at once to fill your receive window. So it's kind of like you think about the sending side of that variable. I was going to ask you what it meant, but then I just put it on the screen. So can anyone read? So I'm sending data on the wire, right? As much as I can send at one time that I'm allowed to send. And if whatever has not been acknowledged yet is, quote, in flight. And once I get acknowledgement, then the bytes in flight goes down until I send more data. So if we look at our little diagram, we have our 256K cat picture file, and we have a 64K receive window. And let's say I send 48K. So of that receive window, I have 16K left, and I have 48K bytes in flight. All right, let's have a look at this real quick. We have to redo this every time. Is this a Mac thing? Should I get Windows? Maybe it's a Microsoft thing, a PowerPoint on Mac. That's what it is. Okay, where were we? So, let's have a look at the beginning of our connection. Three-way handshake. We have a little 24 byte. This is TCP segment length, 24 bytes of data that we send, and then 1460, which is, if we look at maximum segment size is 1460, so that's full size. We send 2, and then we get an acknowledgement. So these two added together is 1484, right? So whatever data we send that's unacknowledged, add it all up, that's bytes in flight, and there's a handy little column you can put. Now, these columns are up to you. That I think most people use probably a lot of overlapping same columns, and bytes in flight is something you probably want to have, especially when you're looking at TCP. And let's see. If you go under the TCP header and under sequence ACK analysis, you'll see bytes in flight, right click, apply as column. You can right click, apply as column, maybe everything. I don't know, just about everything, and add it to your columns up there. So we sent two packets that had 1484 bytes of TCP data. We receive an acknowledgement that acknowledged both of them, and we're back to 0. So we send another 1460 payload. That's how many bytes in flight. We send 3 of them. We're up to 4380. Then we get an acknowledgement, which is acknowledging 2 packets. So it subtracts that amount. And you can see that it continues to grow for every little packet train that we have. And when we get acknowledgement, it subtracts. And so you want to see this number grow over time as TCP does what it does and sends more and more data until it reaches some threshold. So you can see this column is continuing to increase. And as we saw, it's going to grow right up until 64K. Right? No. I answered that. Is there another one? No. Okay. So that's bytes in flight. Pretty straightforward, but it's something you want to keep your eye on when you're looking at throughput performance. All right, let me check all right. Back to here. Now we're going to talk about congestion windows, CWND, something you might see is it abbreviated. This one, sender side flow control. Based on some variable in the TCP header? No, not that easy. Network conditions and capacity. This is something that you cannot find in the TCP header. It is a variable that's maintained in memory on the sending side. It is something is generally referred to in multiples of MSS. And at the beginning of a connection, it can be small, 2, 4, 10, and it will grow. And now the behavior of how it grows and how it changes is something that is controlled by the congestion control algorithm. So depending, there's lots of them out there. You've probably heard of some of them, cubic, Neurino, et cetera. So they all behave a little bit differently. So I'm going to talk about sort of a simplified version, but it increases exponentially during slow start. Then it goes linear after it hits a threshold, the slow start threshold, and it will continue to grow until maybe it fills the receive window or there's packet loss. So to look at it, again, very simplified view. Something like this, right? So you start out with 1, then when that gets acknowledged, you go to 2. When that gets acknowledged, you go to 4, and then you go to 8. And let's say that's the slow start threshold. Then you grow linearly until maybe you hit a network capacity problem. And then the congestion window drops, the slow start threshold drops, and you start over again. Again, this is a very simplified view. It gets much more complicated. The behavior will be different depending on the algorithm, and you might have a different algorithm depending on the conditions. I think Windows, it does automatically. I looked at my Windows the other day, and the TCP profile was automatic. I assume that means it will choose the best one. I don't really know Windows that well to that depth. So the sender is bound by this variable, even if there's space in the receive window. It's not going to exceed its current congestion window, send window, whatever you want to call it, even if the receive window is large. And how the growth in recovery, so we have packet loss and we go into recovery, how it does that, again, as I mentioned, depends on the algorithm. Back when I first put this together several years ago, Windows clients were default Neurino, but I think it may be cubic now. I don't know if anyone has any information on that. So I put both. And Windows Server, again, at the time, I believe was either, I forget which one it was, DC TCP or CTCP. But again, this is all about trying to maximize performance based on the conditions. If you have like do I mention this? I don't think I do. Like satellite, right? You're going to have packet loss, but not necessarily because of capacity, but like a hostile transmission environment. So you don't necessarily want to back off with satellite. You want to keep pounding TCP, so that's its own algorithm. Now, what if you want to know what it is? If you're like troubleshooting, you're to the point where this is the sending side is being weird. I want to know what this is. It's been a pretty good while since I've had to do this, but at the time I did, I used TCP Analyzer on Windows. Does anyone else have another tool that you can see the current congestion window of an active TCP connection on Windows? All right. Well, this one, if it's still around, I used it. And then on Linux, and I assume maybe Mac, you can use SS. If you want to run it during an active TCP session, you can see how it grows or shrinks. So now we have another factor. 256K of beautiful, beautiful cat pictures. We've sent some amount of data, it's been acknowledged. Our window is sliding. Our biggest variable here is 64K receive window. And our congestion window currently is at 33. Again, it's referred to in MSS, so 48K. So on the sending side, we're able to send up to 48K in one go without waiting for acknowledgements. So of the variables, of the factors we've talked about, how much data can we send at once? The minimum of your congestion window, receive window, and BDP. Okay, let's have a look at this. We'll just stick with the same PCAP, I suppose. So let's go back to the beginning, and we'll go in picture form. Do I still have it up? I do. So at the beginning of a connection, we're sending a file. Yes. Thank you. Here we are. Now we're all together. So why don't I just, if I've got 256K, or even if I receive window, congestion window, you know, why don't I just blast as much data as I want? One Wireshark, SharkFest, we had Van Jacobson, and he talked about like how they came up with slow start. Like we had this problem. People were just like blasting data out and falling over each other. And we're like, it's not working. Let's come up with something. And they came up with slow start. And he described the whole process. It's very cool. It's hopefully on the YouTube channel. Go look for it. It's a very interesting talk. But so we're talking about congestion windows. So as I mentioned, at the beginning of a connection, it starts out small. In this case, if we zoom in, we can see one, is that just one little baby packet? No, it was two, that's right. Two little packets, and then it stops. So my congestion window is 2. I stop, await a full round trip time. And again, as I mentioned, it's like exponential, but in real world, it may not always match up exactly to 2, 4, et cetera. But in general, the behavior is that. And this time we have, I think, 3 packets. Let me zoom out. So at that point, that's the congestion window. Then we have 4. Then we have 8. Again, so we send as much as we can, and we have to stop and wait. And once we receive those acknowledgements, we'll increase our congestion window, and we'll send more. And we'll stop and wait. And eventually, and here then we had, yeah, so it doubled. And in this case, we hit the receive window, but at some point the behavior will change and it will start sending a lot more data. Up until some factor. In this case, we hit the receive window. Let me go ahead and switch to this one. Go here, go here. What did I do? See, every time it does that. So again, we can see this behavior where we start out small, and even though we have plenty of space in the receive buffer, our congestion window here in the beginning of us, we have to stop sending and wait for round trip time. We will continue to grow until we hit some condition. This one has a different condition, which we're about to talk about. Okay, any questions? I see something in the chat. I'm wrong on the packet direction. Oh, we have some comments. We don't see the PCAP. Yeah, great. Windows Server 2022 rack is default congestion algorithm. Reno or Cubic for Linux. BBR being the recommendation. Oh, good stuff. Good stuff. And Mac and Linux being Cubic. Okay. So this next one, I think we're good. Now we're going to talk about send buffer. I described the receive buffer, but as an application that's probably sending and receiving, I'm going to have both. If I have to send data, I'm going to have buffer. As an application, I'm going to take data, I'm going to put it into the buffer for TCP then to send. And the size of that buffer can matter. I think the times where I've seen it be a real problem have been usually specific to like either a poorly written application or some weird Windows interaction. Windows meaning the operating system, older Windows. I would say this may not always be an issue, but I'm going to show you how to spot it if it is. So as I mentioned, I'm an application. I'm going to allocate some buffers for reading and writing data. So one of them, I might just take the operating system default, or I can tell it the size that I want. So general, again, the conventional wisdom is your buffer sizes, should be large enough so that you can fill the pipe for BDP. Now, this next bit is something I did this ton of research on one particular problem that I was actually helping Simon Linderman, who's not here, wish he was, with a Tomcat server issue, and trying to figure out why it was slow, and came across this. I don't know if you can see that, but this older Windows documentation, I'll just summarize it for you. But basically, it said if your SYN buffer is not large enough for the BDP, they call it ISB, the ideal SYN backlog, but it's the same thing. Then you're going to have under certain types of IO operations, you're going to have a problem, and that's exactly what we ran into. So now we're looking at our beautiful, beautiful cat pictures, 256K, 64K receive window. Our current congestion window is 33 MSS, 48K, but this really crappy application only allocated a 32K SYN buffer, and we're limited by that. So we have another factor to consider of the factors that we have talked about. And I'm going to show you what it looks like in a PCAP. Before I do, I'm going to do this. Turn this back on. Okay, Wireshark. Let's go back to here. Theory handshake, wonderful, beautiful. We have the client side still using Windows scale 0. Is that a problem? Depends. It always depends. But when you're looking at your PCAPs, you're going to have a process. Probably you'll learn by attending these conferences, by hearing people, and also doing it yourself. You're going to put together your own process. And hopefully it includes looking at the TCP options early on. You're going to go, that doesn't look good. Is it the problem? I don't know, but I'm gonna file that away. If it's a throughput issue and I'm receiving as a client, yes, it's likely a problem. But if I'm sending, who cares? On the quote server side, the Synax side, we have a window scale. Okay, fine. We see a similar behavior, a little 24-byte payload, and then full size. In my experience, based on the port number and that little 24-byte packet, this is like iPerf2, and we have some throughput. We see bytes in flight going up. We see a bunch of acknowledgements coming in, more bytes in flight. So let's go back to our nice picture. So we have our slow start. We send some data, we wait, we get acknowledgements, we increase our congestion window, we send more data. Our little packet train is getting longer and longer each go around. We still got plenty of room in the receive buffer, no problem. And then it switches behavior, and you can see the sending behavior switches, and it just blasts out some packets, and then it stops. Okay, fine, maybe it hit its current congestion window, fine. We see acknowledgements come in as this line goes up, it sends out more data, and it stops. I don't know, to my eye, those look pretty much the same length. I don't know that we sent more in this go around, in this round trip. And we see that same amount of data being sent every round trip. Occasionally you get like a weird little break here, but it's still pretty much the same amount of data. And we're not hitting the receive window, no packet loss to bring down the congestion window. So what's the limiting factor here? Now, if you go back to our PCAP, so let's look at these are all acknowledgements coming in. And then we start with bytes in flight at 1460. So we got a brand new packet train, right? 1460, we're sending this data out, It's going, and it stops. Right about 128K, right? And then acknowledgements come in. We send like one in the middle. Sometimes we see that, but essentially all the acknowledgements roll in, and then we start a new packet train. And it goes, and it goes, and it goes, right around the same And we see this behavior over and over and over. And we ends on a push bit, meaning generally on the sending side, the push bit can mean the end of a buffer. So we're emptying our buffer, we're waiting round trip time, and we keep doing this behavior over and over, and it never, bytes in flight really never get over this amount, right around 128K. You see this behavior over and over again, and you go, I don't see anything else that should be limiting to this. This looks like a sending application issue. And you go look at the configuration. You find the man page or documentation, and you see, oh, it has a default buffer size, send buffer of this. Let me go bump it up in the configuration, restart the application, problem solved. I've seen this a handful of times, either something, a server side that you can fix, or it's some proprietary horrible application that good luck working with the vendor trying to get it fixed. Maybe you will. All right, that is send buffer. Now we're gonna wrap this up. Okay, so again, we've kind of worked through a series of factors. So here's sort of a way you can think about it. One, try to know what the BDP is. What is the bandwidth? What is the latency? Kind of know what you're aiming for. What is the best case scenario? Then on the receiver side, what is the receive window that it's advertising? Sometimes it might start small and it might grow. It's sort of auto, it will grow as the throughput increases. It'll start small but get bigger. Sometimes it'll just stay big from the beginning. But is that the limiting factor? Is the receive window the limiting factor? You'll see, TCP full window in the expert info, or if you're looking at the TCP trace, you'll see the line, the packets touch the line. So look at your bytes in flight. Is it growing? So is our congestion window increasing with each round trip? Is it trying to, reach capacity? Is it continuing to send more and more data? Or if not, as we just saw, does it stop and wait for the acknowledgements to come in and then send the same amount of data over and over again? Or is there packet loss, or you see retransmissions, duplicate acts, so that the congestion window is prevented from reaching its full potential? Let's look at that real quick, what that might look like. Let's see, that's a different PCAP. Okay, so three-way handshake. 1460, we have a window scale there. We have a window scale here. It's small, but is that a problem? I don't know. We're getting, this is HTTP, we're getting a 100 meg file. And the data starts going, right? Let me click on an ACK and see if that fixes the thing. Let's look at our little picture. I did. Okay, so remember, this is bytes over time. So we want to see it up into the smooth and up into the right. We've seen a bunch of weird pictures today because all these have problems that were, none of them are like good examples. This one looks different, right? It's like, it's wavy. And if the slope of the line indicates a throughput. So if we kind of go to the beginning, we can see this really nice, sort of textbook example, right? Slow start. We send a little more data each round trip. As I mentioned, sometimes you'll see the receive window start out small, but as the throughput increases, it will grow the receive window as well, which you can see happening. And as we reach, this point up here, we start to really start sending more and more data, and we're kind of reaching this data going out, acts coming in consistently, and throughputs, really it's building up. The line is going further and further up. Let me zoom out, and then you see it where it changes direction. And you see a bunch of stuff. Anytime you see these red lines, those are selective acknowledgements. Won't go into a lot of detail about that. You may already know about it, but it means packet loss, generally. this many red lines, yeah, there's going to be some packet loss. So as we talked about, congestion control kicks in. We reduce our congestion window, and the slope changes. The slope of the steeper the line, the more throughput. So if it goes flatter, that means we reduce throughput. And you can see we're sending less data each time. We have a little more packet loss, and it gets even worse. But look, oh, it's okay. We're doing all right. We're ramping up again. We're starting to go faster and faster. We hit more packet loss, and the line flattens out again. So this is what packet loss looks like and how it affects your throughput. You ramp up, you hit some threshold, fill a buffer, some packets get dropped, whatever it may be, and your throughput's going to drop. We have a question. You said push bit on the sending side can mean end of the buffer. Doesn't push bit indicate to receiver to send data quickly to the application without buffering it? Both things can be true. So if you think about perspective, if I'm a receiver and I receive a packet and the push bit is set, then yeah, and maybe I'm going to flush the data to the application. But from the sending side, it also has an implication. It means generally it can mean if I have a buffer that I'm putting data into, then when all that data is sent from that buffer, the last bit of data, the last payload will have the push bit set. So it can be, you can infer sometimes that that's it can give you information about the size of the buffer that's being used on the application, but that's from the sending side perspective. So it means the same thing. I mean, they're both are true. Answer live. Done. Can you do this with SSL VPN traffic? What does this mean? I'll let you come back on that. There is a session tomorrow, Hansong says, on troubleshooting VPN. Please jump on that one. All right. So we just looked at congestion, what that looks like. But if all these are yes, great, fantastic. So let's talk about a few other things. What are we missing? What have we not talked about? And we're not going to go into a bunch of detail because the details are, there are many. We're talking about the big rocks. So what are some other things that you know impact throughput? Meaning, always be sending data, but I'm not. Say again? Oh, 5 minutes. I'm like, I don't know about that TCP thing, 5 minutes. That means wrap it up. All right, delayed ACKs, right? So we talked about ACK every other packet. If I get one, how long? I'm waiting for a second one. Well, how long do I wait for the second one? That's a delayed ACK. If you couple that with, on the sending side, Nagel algorithm, which is about, do I have enough data to send or do I wait for more data from the application? Those two things together create a problem. If you want to learn all about this, Hansong has a video on his YouTube channel that will walk you through the whole thing and you'll understand why it's such a problem. What else? How about so bytes in flight is 0. So we've sent some data, it's been acknowledged. There's no data on the wire, but you see like a 5-second delay. Is that a problem? Like what could that be? Any thoughts? It depends. That's the correct answer. Say again? That's true. That's true. But let's say all the acknowledgements have been received. There's no outstanding data. Maybe there's an issue on the application side. Maybe it's doing something. It's crunching some data, doing some calculations. Maybe there's the host is, it's got a slow disk. Maybe it's talking to maybe it's querying a local database and you don't see that traffic. Who knows? But TCP's done its job. So at that point, it's either application, it's a host, maybe it's user interaction. Maybe if it's web, they're like reading, waiting to click on the next thing. But from the transport layer, it's done its job. It's something else. And it may not be a problem. What else? Proxies. So I've been in the proxy business a long time, from WANopt, now Zscaler. For me, if I'm troubleshooting that scenario, then I want to see, if I can, PCAPs on both sides, right? What does the performance look like on this side? What does it look like on the other side? Is there latency going through the proxy? Sometimes I see, a proxy in the middle sending 0 windows. People go, oh, there's something wrong with, this proxy, it's sending 0 windows. Well, maybe it's receiving data very quickly, but it can't drain it very fast. And there's a problem with the receiver on this side, or there's packet loss here. So it has to tell who it's receiving data from to slow down. So the problem isn't necessarily on the proxy, it's downstream. So you want to see both sides to be able to understand where the issue might be when there are proxies. Last thing, buffer bloat. You may have come across this where if you think about your bandwidth, your BDP, maybe it's a single lane highway for cars, right? But you have a huge parking lot off to the side with hundreds of cars waiting to get on. You can essentially trick TCP into thinking that there's more bandwidth than there really is, and you're happily sending along. And then once buffers fill up, it all comes crashing down. So these are topics that I've covered here that you can go and look up more. Last thing, you didn't know there was going to be a quiz, did you? So I encourage you to go here, packetbomb.com, SF22-quiz. And it looks like this. Make sure you, God, it doesn't look like that. All right, it looks like this. Make sure you click here and download the PCAPs before you start the quiz. There's only 10 questions. Some of them are just like multiple, answer the thing based on what we've talked about. And then the second half, or the last few, or I don't know, however many it is, you'll need to, it'll say open PCAP 1 and answer this question, or open PCAP 5 and tell me why it's slow, but it's still multiple choice. So I encourage you to do the hands-on to try to apply what I've been talking about this whole time. Oh, thank you, Betty. It's in the chat. Okay, I am done. There is a survey. There's a survey, so do that. You can, I'm on Twitter rarely, but sometimes, probably more this week, but you can email me as well if you want to talk about packets. I'm happy to. And any questions? So this topic, this is a rabbit hole. We've talked about the big factors, where you can start, but it's a rabbit hole you can go down. Survey link, yep. All right, no questions, no questions. Love you, Kary. All right, hey, thank you, love you. Thanks everyone for coming. Have a great time at SharkFest. We'll see you next time.